Hi guys, Mr. Rocco here. I hope you had a great weekend. This will be the first video for this week, and there are 4 assignments that go with this week. One is called Specific Heat Worksheet that has 10 questions. The second one is Latent Heat Worksheet that is another 10 questions. Then there is a Topic 4 study guide. We are finishing up Topic 4 this week. So the study guide is also an assignment, and Topic 4 vocabulary. Again, when you write the definitions or type the definitions, use your Earth Science Dictionary that you should have. If you lost that dictionary, there is the same exact dictionary in the back of your orange covered UPCO Earth Science review book that you should have at home. So look toward the back of that book, and there's a dictionary back there where you can look up the terms. Do not use Google. Okay, because you're getting, those are different definitions. Okay, so let's get right into temperature versus heat. So temperature, if it's hot outside or it's cold outside, when you measure temperature, you're measuring atoms, and you're measuring how fast these atoms are moving. So it says temperature measures the average vibration rate of atoms in a substance. So it's how quickly the atoms or molecules are moving, whether it's in the air, whether it's in the water, etc. That's what temperature measures, how quickly molecules move or atoms move. There's 3 scales of temperature: Kelvin, Celsius, and Fahrenheit. This, of course, is a thermometer, and I'm going to play this video for you on YouTube how thermometers work.
You're feeling woozy. Maybe your forehead feels hot. You stick a thermometer in your mouth, but it comes back 37°C. Or it comes back 38°C. You're running a fever, call in sick. But if it comes back at 40°C, get yourself to the ER. We have a lot of confidence that we're measuring temperature accurately. 1 or 2 little degrees can literally mean the difference between calm nerves and a medical scare. Knowing temperature is important beyond your health too, whether it's setting the grill for the perfect burger or figuring out what hot outfit will keep you cool at a summer cosplay event. You can often proceed informed because of our trust in modern thermometers. If I told you thermometers don't measure temperature, would you find your trust shaken? Thermometer means measurer of heat, but that's the same thing as temperature anyway, right? Well, scientifically speaking, no. But knowing about heat can tell you about temperature if you're clever. Temperature describes the average energy of the molecules in a system, while heat describes the transfer of energy between systems that are at different temperatures. Thermodynamics tells us how heat moves around in its first 3 laws. 0, heat is the same regardless of how it's measured. 1, heat cannot be created or destroyed. And 2, heat moves from hotter to colder. Yeah, that list starts at 0 because that part was figured out after 1 and 2. Anyway, armed with these laws, we can understand how thermometers work to make them as useful to us as possible. Consider the bulb type, that liquid in a glass tube thing you know and love. Imagine it's in the freezer. The thermometer loses heat to the surroundings. That means the molecules in the liquid slow down, and the liquid contracts, pulling its level down the scale. Move it over to the sauna, and the thermometer gains heat. This causes the molecules in its liquid to move faster, so the liquid expands and the level moves up the scale. When the thermometer is steadied out, both it and the surroundings are the same temperature, which means, thanks to thermodynamics, the thermometer tells us what the temperature is. We've been playing around with simple up-down thermometers for hundreds of years. What up, Galileo, Fahrenheit, and Celsius? Some clever physical chemists and engineers have given us all kinds of thermometers you see today. So let's take a little tour. Many people associate trusty bulb thermometers with the mercury. Before we learned that mercury exposure could lead to health problems, this liquid metal was preferred because it expands and contracts at a constant rate and stays liquid over a useful range. And it sort of looks like the T1000, which is very cool. But finding silvery bulb thermometers is rare these days. That's not exactly a new trend, because even before mercury thermometers, some early adopters used red wine because its alcohol content protected it from freezing, and it was easier to see in glass than quicksilver. Nowadays, most bulb thermometers use ethanol, this dyed red, and sometimes blue. One of the most common electrical thermometer is a thermistor. These are a resistor that conducts electricity differently as temperature changes. Thermistors are made from metal oxides like manganese or say iron, or semiconductor materials like germanium or silicon depending on the temperature range. And they're often embedded in a glass bead with wires sticking out. These can be made at very low cost, meaning they're often what's inside a digital thermometer that you might have stuck in a mouth recently, checking if you or someone else has a fever. It's worth noting that electricity-based thermometers are still using thermodynamics, but using moving electrons, electricity, gets us into the quantum realm. Sound a little sci-fi? Then check out this action at a distance option. Some metalloids and metals produce electricity when light shines on them. Explaining this got Einstein a Nobel Prize, and the world got light sensors and solar cells. All objects give off a sort of light called infrared radiation, or IR. Indium, germanium, and other semiconductors will produce electricity when IR hits them. So pointing them at, say, a child's aching ear or a simmering pot of stew, the semiconductor detector converts the radiation readings to temperature on a digital readout. You may also recognize infrared sensors in the form of heat-seeking cameras used in hunting, warfare, and cryptozoology missions to track down Bigfoot. Measuring temperature through radiation readings can reach far. Satellites scanning Earth measure its temperature from thousands of miles up. So satellite thermometers in orbit are essential to understanding our climate. And one day, they could routinely tell us about other planets' climates, so you could figure out what to wear when you got there. Want to know more? Tell us if you want a video about triple point or any other physical chemistry wonders. And while you're at it, check out these temperature-sensitive reactions episodes. Thanks for watching.
Okay. So in your Earth Science reference table, there is a temperature scale, actually all three, Fahrenheit, Celsius, and Kelvin. It's on page 13. And let me pull that up here. Just be very careful, excuse me, when you have to convert. The Fahrenheit scale on the left-hand side, excuse me, these little lines on the left count by twos. So, for example, this is 80 degrees Fahrenheit. The next little line up is 82, 84, 86, 88. This would be 90 right here. And then 92, 94, 96, 98, 100. So be careful. Fahrenheit counts by twos. The Celsius and the Kelvin scales count by ones, the little lines. So if this is 20, then it goes 21, 22, 23, 24, 25, etc. Kelvin, same thing. If this is 310, let's say right here, this would be 311, 312, 313, 14, 15. So you got 1 degree for Celsius, 1 degree for Kelvin, but counting by twos for Fahrenheit. So they might ask you to do that on an exam or even on the Regents where you have to convert. They also give you some special numbers. So if you look, for example, let me go back. Water freezes, room temperature, and water boils. Now, water freezes is the same as ice melts, right? What's the difference? Freezing water, you have to remove the heat, right? To freeze something, you have to take the heat out. To melt an ice cube, you have to put heat in. It's the only difference. It happens at the same temperature. When an ice cube melts, or you take a tray of water and put it into the freezer and make ice cubes, it's all happening at the same exact number. It's just, are you putting in heat or are you taking out heat? But it happens at this number, these numbers right here where this line is. And so if you look, you'll see 0 Celsius, which happens to be 32 Fahrenheit and 273 Kelvin. If you come up here to this red line up top, that's water boils. And again, that could be making the liquid into a gas, right? Boiling or evaporating, or turning the gas back into a liquid. That's called condensation. So that, again, happens at the same spot, at the same temperature. 100 Celsius, which is 212 Fahrenheit, or 373 Kelvin. And I think I have that on these, yeah. Let me pull away these boxes. So these are important numbers. And again, you don't have to memorize them. They're right in the reference table. So ice melts or water freezes. Again, same spot on the chart. 32 Fahrenheit, 0 Celsius, 273 Kelvin. Water boils, and this should say a water vapor condenses or gas condenses at 212 Fahrenheit, 100 Celsius, or 373 Kelvin. All right, so the gentleman talked about in the YouTube clip the difference between temperature and heat. Temperature, again, measures how fast molecules move. Heat is a transfer of energy when you have two objects at a different temperature. And that was what we did last week. Remember, we talked about source versus sink. Source is always something hot. A sink is always something colder. And so once you have a difference in temperature, source to sink, heat is going to flow from hotter to colder or from source to sink. So heat is just the energy needed to make the molecules move. You can't measure heat with only a thermometer. It says heat is measured by observing the change in temperature of water that a hot object was placed into. So if you had some kind of, let's say, hot piece of metal rod and piece of metal and you put it into a glass or beaker of water, there's a source sink reaction. The heat's going to leave the hot object and go into the water. And then you can measure how much heat went into the water. And there's an equation that goes with that. And that's what I'm going to talk about here. So heat is measured in a unit called a joule. Joules. Joule. Joules. So they're called joules. And there's three things you have to multiply. You have to multiply the change in temperature of the water. So how many degrees did the water go up or down, temperature, times the mass of the water. How many grams of water do you have? And then there's a special number. Every substance has a certain amount of heat that it needs to raise its temperature or lower its temperature. It's called its specific heat number. These numbers are right on the reference table, actually on the first page. If you look on the front cover in the upper right-hand corner, you'll see a chart that lists some common materials and their specific heat numbers. So again, I'll go through that one more time. You need to multiply the change in temperature of the water. How many degrees did the water go up or down? Times the mass of the water. How many grams of water do you have? Times the specific heat number of whatever the substance is. In this case, if you're dealing with water, it'd be water. The instrument that's used to measure heat is called a calorimeter. And I have a picture I'll show you of them coming up here in a minute. These are specific heat numbers. So this is on page 1 of your reference table. And so you notice the units. It's how many joules of heat are you putting into something or taking out. It's how many joules / per gram per degree Celsius. So it's how many joules for every gram of a substance, for every degree you want to change the temperature of that substance. And they list them in the reference table from the highest joules to the lowest joules. So liquid water has the highest number. And these are common materials. Now, this is only, 1, 2, 3, 4, 5, 6, 7, 8, 9 materials, right? Other things are not listed here, but you have 9 common materials with their specific heats. So liquid water has the highest number. It takes a lot of specific heat there. So you need 4.18 joules of heat for every gram of water, for every degree you want to raise the temperature. Or, again, if you want to freeze something, how many joules you have to take out of that water to freeze it. Ice doesn't need as much. So solid water is 2.11. So about half the amount of joules are needed when it comes to ice. Water vapor, that's obviously water in the gas phase. That's close to ice, a little less, 2 joules. So you can see right away the first 3 things are water in the 3 phases. Liquid water, solid water, and then gas water, water vapor. Then you have air, but this is dry air. No moisture in the air at all, 1.01 joules. Basalt, which is a type of rock. That's an igneous rock. We'll get into rocks later on in the year. So that's 0.84 joules. Granite, which is also a type of rock, 0.79 joules. And then you have a couple of metals at the bottom, iron, copper, and lead. Very low specific heat numbers. Iron is 0.45 joules, copper is 0.38 joules, and lead is 0.13 joules. These are calorimeters. You actually have 2 calorimeters here. And I normally do a lab with this. I don't know. We'll see about doing the lab this year. It's possible. Where what I do is students will have 2 cups. I'll fill this cup over here. This is a calorimeter with cold water. This calorimeter will be filled with hot boiling water. This black line, thick black line, you see, this would be an aluminum bar. And this is also to show conduction. If you remember last week, conduction means contact, touching. And so what happens is you fill this cup with cold water, this cup with hot water, you put a insulated lid on top and a thermometer. You kind of let the thermometers adjust, and so they start at a certain temperature. Like normally this thermometer, the cold might start at, I don't know, let's say 12 degrees Celsius. The hot water was boiling, but by the time you get it in the cup and start the actual experiment, it might be about 90 degrees Celsius. And again, this is to show source versus sink. So your hot water is your source and your cold water is your sink. And then you take the aluminum bar and you put it into each cup of water. That right away, you're going to start a reaction, right? That's source to sink. The hot water is going to lose heat. So the heat will leave the hot cup and it's going to travel through this aluminum bar and it's going to go into the cold cup like that. And that's called source to sink. So the hot is the source, the cold is the sink, and you're going to start to see energy transfer. The hot temperature will go down. Usually I have the students take 1 minute readings. So every minute they're going to read the temperature of the hot water. So after a minute, this might be 89, and then 88, 87, etc. The cold water temperature, because the heat's leaving the hot and going into the cold cup, this will start to go up. The cold might be 13, then 14, then 15, etc. And then we graph it. It's a very simple lab. We'll see if I can try to get that set up somehow to do in school, because that's a pretty basic lab, pretty good lab. Now, if you want to measure how many joules were gained or lost by each cup, so normally, I'm going to go back to the lab. Normally what I would do is run this for about 20 minutes. And I would say, okay, let's say the hot water started at 90. After 20 minutes, let's say the hot water cup got down to 60 degrees. So I'm just using this as an example to help us with the next part. So the hot water started at 90, dropped down to 60. So that's a difference of 30 degrees. So I know the hot water went down 30 degrees. The other thing I also need is how many grams of water. So we would fill this, let's say, with 200 grams of water. So you would know that out of the start. That's like a control. So you had 200 grams of water. The hot water went from 90 down to 60 degrees, so it lost 30 degrees. And then I'm going to look up that specific heat number of liquid water, which, let me go back, it's right here, 4.18 joules per gram per degree. If I know all three of those, I know the number for water, specific heat number, I know how many degrees the hot water went down, and I know how much mass of the water, 200, I can calculate the joules, the amount of heat that, in this case, the hot water lost. I could also calculate, and again, I have students do the same thing, the cold water. Let's say the cold water started at 12 degrees, and after 20 minutes, the cold water was up to, I don't know, let's say it went up to 30 degrees Celsius. So that's a difference of 18 degrees. So I would know, okay, the cold water went up 18 degrees. I also had 200 grams of cold water. And again, I know the number for water is 4.18 joules. I could then figure out how many joules of heat did the cold water gain. So over here, the cold water is going to gain, right? And the hot water is going to lose. That's that whole source to sink. And I can calculate those joules. So here's the actual equation. You need the change in temperature. How many degrees did something go up, or how many degrees did it go down? Again, times the mass of that substance. In that case, I was dealing with liquid water. And then I need that specific heat number off the front of the reference table. So here's those numbers again. I threw a couple of other numbers here. They're not listed on the reference table. I've discussed with kids. Sometimes I get kids that are into like electrical and wiring and doing stuff like that. And there's a thing called solder. I don't know if you know what solder is. When you, let's say you have two wires and you're going to fuse them together, and you use solder to, after you twist the wires together, you want to solder them together. It's a silvery material. It's actually tin. Has a very low specific heat. Now, I didn't mention this before, but I'll mention it now. The rule of thumb, when it comes to specific heat, notice liquid water has a very high number, 4 point. Again, these are listed from the lowest going up to the highest. What does that mean? Because liquid water needs over 4 joules for every gram, that's a very high specific heat number. That means the higher the number, the longer it takes for something to heat up, because you have to put more work in, right? Notice water needs 4 joules, over 4 joules, 4.18 joules to heat up every gram of water every degree. That's a lot of joules. And so that means it takes a lot of energy to raise the temperature of water, liquid water. Something like solder, and again, if you've ever worked with solder and done any kind of wiring, I usually get some students say, yeah, Mr. Rocco, I've done that before. That's cool. Solder's number is very low, 0.21. And if you ever work with solder, you take a little bit of heat, barely, you just touch it, barely just touch the solder, it melts very quickly. And you want it to do that. So then it turns into liquid. It then kind of pours all over the wires. Then you take the heat away, and what happens to that solder? It hardens very quickly. So that's the rule here. The lower the number, the faster something will change its temperature. It's going to heat up fast. It's going to cool down fast. Okay, so the lower this number, it means it doesn't need a lot of heat. 0.21 is 1/5 of a joule. That means it needs a very little amount of heat to raise its temperature. So things that have low specific heats, lead, copper, iron, these things heat up very quickly. I don't know if some of you maybe have them in your kitchen. People that use copper frying pans, copper pots and pans, very expensive. Oops, my thing wants to do a restart. What's going to do snooze? Sorry about that. So a copper pot and pan will heat up very quickly. So some of you might have copper pans at home. You put just a little bit of flame on that copper pot and pan, it's going to heat up very quickly because it has a low specific heat. It doesn't take a lot to heat up copper. But also, again, when you turn off, let's say you have a gas stove and you shut off the gas stove, the copper pan will cool down quickly. Again, very expensive copper pots and pans, but for that very reason, that they take very minimal heat to heat up and very minimal heat to cool down. Okay. I always use the water analogy here. Let me reset this. If you think, and this is just common sense, if you had, let's say here, we're in my classroom and I got my table and I put an ice cube on the table. I just set an ice cube there. Will that ice cube melt in my room? And most of you would say, yes, it would. And I say, where does it get the heat from? Well, it's getting it from the air. So the air has enough heat in it to do source to sink. The air is going to lose heat. It's going to throw heat into that ice cube. And all of a sudden, Mr. Rocco's going to have a nice puddle of water sitting on his table as the ice cube melted. It didn't need a lot of heat. 2 joules, 2.11 joules. That's not a lot of heat to melt that ice cube. There's enough heat in the air to melt an ice cube. But if I said, hey, I have a beaker here. I put a beaker, fill it with water. I want that water to boil. I want to raise the temperature with the air using the heat in the room. Is it going to be able to boil? Most of you say, no, Mr. Rocco, that's silly. I got to put some kind of hot plate underneath or a flame underneath, some kind of source of heat under that beaker water to get it to boil. Exactly. That's common sense, right? I need twice as much, 4.18 joules. There's not enough heat in our air to boil water. There's enough heat in the air to melt a cube. I can raise the temperature of a piece of ice and melt it, but I don't have enough to boil water. So think common sense. All right, let's go to an example of joules. It says how many joules are needed to make 25 grams of water change 3 degrees Celsius. And again, the equation is here. You need the change in temperature, which we know. I'll circle it, 3 degrees, times the mass of the water, which we also know from the problem, 25 grams, times the specific heat of whatever substance you're doing. In this case, I'm dealing with liquid water. So my number, again, I'll go back. Liquid water is 4.18 joules per gram per degree. So when I set this up, I'll do it up here. It's going to be 25 grams, that's my mass, times I'll do my change in temperature, 3 degrees Celsius, times the number for water, liquid water, which was 4.18, and the units look like this. Joules, J for joules, slash, on the bottom is grams degrees Celsius. Now, why units are important? Because remember, you're looking for J, you're looking for joules. Notice these G up top. This gram is on the top, this gram's on the bottom. Units cancel units, so this gram's going to go bye-bye, this unit's going to go away. This Celsius is on the top, this Celsius on the bottom. Cancel out. What am I left with? J for joules. That's what I want. And then it's just a simple multiply. 25 times 3 is 75. Let me grab my calculator. I'm going to do 75 times the number for water, 4.18. I get 313.5. So if I had 25 grams of water, and I want to make its temperature rise 3 degrees, I have to put in 313 and a half joules. And hopefully that's the answer behind that box. Yep, 313.5. So again, just to remind you, you take the the change in temperature, whatever that temperature went up or down, in this case 3 degrees, times the mass of, in this case, the substance, which was 25, times the number for whatever substance. Now, if this didn't say water and this said iron or copper, I would have gone to my reference table and I would have picked one of these numbers: iron, copper, lead, whatever substance they put into the word problem. So just be aware of whatever's in the problem. In that case, I said water. And when they say water, it's implied liquid water. If it wasn't liquid water, they would have said ice, or they would have said water vapor. But in this case, when they say water, they imply liquid water. But it could have been any substance. I could have picked basalt, granite, iron, any of these. Any of these could have been here. Then I would have used not the 4.18. I would have used whatever number off the chart, my reference table here. These would have been the same. Still 25. Still 3. This number would have been the one number that would have been different, depending on the substance. It says all substances require their own, again, specific amount of heat. And that's why it's called specific heat, because every substance has its own specific number of energy that you need to put in or take out. It has to be gained or lost to change its temperature. So every substance has its own specific number. That's why they're called specific heats, because they're specific to that substance. This is called specific heat. The joules of heat needed, again, to raise or lower, because you're either going to put in heat or take out heat, the temperature every gram, every degree. So it's per gram per degree. Some substances require lots of joules, and again, the higher the number, like liquid water, they heat up slowly. And because they need a lot of heat, they cool down slowly. They have a high specific heat. Name one thing that you use on the stove to cook, and that's liquid water. So it takes more energy than any other substance to heat up and cool down. So again, liquid water, you need 4.18 joules per gram per degree. Common sense. Pretend, and I'm a horrible drawer. Let's say this is my stove. And let's say I have, my burners on the stove. Okay, I'm doing this with a mouse, so excuse me. So let's say I put a pot of water on the stove. There's the handle. Okay, I got water in here. I turn on the flame down here. If you ever boil water, right, does water boil quickly? No. It takes a long time to boil water. There's an old expression, a watched pot never boils. A watched pot never boils. What does that mean? It means you put a pot of water on the stove, you're in a hurry. I got someplace to go, right? And somebody says, well, let me cook for you, mom, dad. Somebody says, I'm going to cook pasta, right? Okay, pasta's probably not the thing you want to cook when you're in a hurry. But you put the pot of water on the stove and it takes forever, and you got to wait, and you got to wait, and you got to wait, and you got to wait for the water to boil. Now, why? It took a lot to heat it up, right? 4.18 joules. However, let's say you get the water boiling. Now shut the flame off. Shut off the stove. Walk away for 10 or 15 minutes. Come back later. And you try this at home. All right? Just don't burn your finger, please. Shut off the stove. Go back. 10, 15 minutes. Just gently touch the water. Is it cold? No. It's still kind of warm, right? Why? Because it takes a long time to cool down. Because something that takes a lot to heat up, once you heat that thing up like water, it's going to retain the heat. It's going to hold on to the heat. So liquid water is very good not only at, it's slow at heating up, but once it is hot, it's going to keep the heat. Okay. I used to work in restaurants. I worked at Foster's when I was a teenager in town. CJ's Pizza up on 990. Used to work there way back when. If you ever go into a kitchen, a restaurant, a diner, and you go in the kitchen, when they put soups and gravies and stuff like that, they put them into a hot water bath. So you'll see metal pans, and they'll put the soup, the gravy, the sauces and stuff are sitting in hot water. Why? Keeps them warm, keeps them hot, right? You don't want cold soup, you don't want cold gravy, you don't want cold tomato sauce. So they put it all into these hot water baths, and the water keeps them hot. Caterers, if you ever had a party and you had a caterer cater the party, they come over, they put trays of ziti, lasagna, chicken parm, etc. They put them in aluminum pans, and then what's underneath? They fill a water bath with it, and then they put the little sternos underneath. That sterno is just giving it a very minimal amount of heat. It's not causing it to boil, but you want to put it in the hot water bath to keep the food hot, because you've got a party and you want to keep the food hot for hours while you're serving your guests food. So water is a big substance when it comes to keeping things warm and keeping food hot and things like that. And again, why? Because it has a high number, high specific heat. So not only does it heat up slowly, but it also holds on to the heat. It cools down slow. So this is just the definition of specific heat. The joules, again, needed to raise or lower the temperature 1 gram of an object 1 degree Celsius. This just says, look on page 1 of your reference table, which heats up and cools faster. So if it says it cools faster, you want the lower number, right? Because remember, the lower the number, the faster it heats up. So compare lead to iron. Here's the chart. Notice lead is lower. And the nice thing with the regions they did on the reference table, they put them in order from the highest to the lowest. So if you compare lead to iron, you can see lead is lower, so lead heats up faster. Copper versus granite. Here's granite, here's copper. That's going to be copper. Dry air versus basalt. Dry air is here. Basalt's just below it, so it's going to be basalt. Ice versus liquid water. Again, ice is below, so ice heats up faster. You have seen the effects of water's high specific heat, especially if you go on vacation. Where? The beach, right? You're standing at the ocean. You're standing at the biggest pool of water you possibly can. So you have seen the effects of, because water takes a long time to heat up and a long time to cool down, this high specific heat idea at the beach. Let me show you what I mean. It says, let's go to this. Sea breeze. Let's say it's daytime. So sun came up. You're going to go to the beach. It's a summer day. It's July. Let's fast forward to July. It's a summer day. You're going to the beach. Sun comes up, sun's going to start heating up the air, and the sun's going to start heating up, sun's going to heat up the water, and the sun's going to heat up the land. Well, water, because of that high specific heat, takes a long time to heat up. The land has a lower specific heat. Sand heats up quicker, right? Step on the sand. You go to the beach, you forget to put your flip-flops on, your sandals, you step on the sand barefoot, right? Ow, ow, ow. You're burning your feet. The water doesn't happen that way, right? The water takes a long time. So what did you just create? You created a difference in temperature. The water is cold air. The air above the water is cold. The air above the beach is warm, is hot. And we haven't done weather yet. That's coming up starting next week. Difference in temperature in the air creates a difference in pressure. Cold air is normally high pressure. When you look on a weather map and you see a big blue H, that's high pressure, which is cooler or colder air. When you see an L, low pressure, that's warmer air. And then you create what's called a breeze and wind. Wind is created by a difference in pressure. And again, we'll cover more of this when we get into weather. So you've got cold air sitting above the cool ocean water. You've got hot air, warm air sitting above the sand that heated up quickly. You created a high pressure over the ocean. You created a low pressure over the beach. That creates a breeze. Wind is like energy. Remember we said energy always goes from hot to cold, from a higher temp to a lower temp? Well, wind does the same thing. It always goes from a higher pressure toward a lower pressure. So in this case, the breeze is going to blow from the high pressure this way toward the low pressure. That's going to create what's called a sea breeze or an onshore breeze. The cool air is going to come off the ocean and hit you standing on the beach, right? Think about it. Why do people go to the beach in the summer? To cool off. You get that nice cool ocean breeze. Now that's going to happen during the day. The sun's out. Nighttime, different story. If you ever go swimming at night, What's it like? Well, and most kids will tell me, Mr. Rocco, you go swimming in the pool at night, you get in the water, it's kind of warm. You get out of the water, you're freezing. I jump back in the pool, right? It's actually warmer in the water than it was when I got out of the pool. Exactly. Again, why? Because now you have water holding on to heat. So this is nighttime. Remember I said water takes a long time to heat up, but once it has that heat, it holds on to that heat. And so at night, the water is cool slowly, slow to cool. That's what I meant. And so the water will hold on to that warmth. And that's why the warm air is now sitting over the water. The land has a low specific heat. It heated up quick, but it also cools down quick. So the land is going to be cool air. And what did we do? We basically switched the warm air and the cold air masses. They flipped. Now the cold air is on the land and the warm air is on the water, and we switched the pressures. The high pressure, which is cold, is sitting over the beach. The low pressure is sitting over the ocean. And the breeze will, and it doesn't happen instantly. It's not as soon as the sun sets. You got to give it a few hours. All of a sudden, the breeze is going to blow the other way. And now you get what's called a land breeze or an offshore breeze. The breeze is blowing from the beach out into the ocean. And so you have what they call a land breeze. Wind is named for the direction it comes from. So when it said, like, let me go back. This said sea breeze. That's because, well, it's a big mess. The wind was coming from the sea going toward the land. When it goes the other way, right, it's called a land breeze, meaning it's going from the land out to the ocean. And so you switched. And all of this only happens because water cools slowly. It takes a long time because of its high specific heat. It heats up slowly, but it also cools slowly. Wintertime. Now that's on a daily basis. You can look seasonally. Rhinebeck is a good 100 miles from the shoreline, so we tend to get more snow in the winter. But if you go to places like Long Island, especially the south-facing shore of Long Island, they don't get as much snow. Let's say this is the south, you're right here. This would be like Jones Beach area. They get less frozen precip. They might get more of a rain or a mix when we get a snowstorm up here in Rhinebeck. And that's very typical. Why? Because they're closer to the ocean, and that keeps their temperatures not as cold. So they don't get as cold especially on the south-facing shore. You might get a little more snow on the north shore, but the south-facing shore is always going to be a little slightly warmer than Rhinebeck, and we're 100 miles inland. We get 6, 8, 10-inch snowfall. Let's say the South Shore of Long Island might get a dusting, and then it flips over to mix, and then eventually to rain, because that warmer ocean influence, the water temperatures keep their temperatures not as cold in the winter as we do. Same thing again in the summer, the opposite. Again, why do people in Rhinebeck leave here and say, it's so hot inland? Yeah, Rhinebeck can get up to 100 degrees, right? So we're 100 miles inland, and it's a hot day in August where it's 100 degrees. You drive down to the Jersey Shore or Long Island, and now it's only 80 degrees at the beach, right? You could have a 20-degree drop in temperature because you're getting that nice cool air coming off the ocean in the summertime. You go to places like Jones Beach. So again, the ocean has a big influence on your temperatures. It's not going to allow locations, if you live close to the coast, you're not going to get as hot in the summer, and you're not going to get as cold in the winter. And there's actually a term for that. It's called moderate living. So moderate living, that's not us. We are too far away from the ocean. We're 100 miles inland. But if you live on the shore, Jersey Shore, Long Island, places like that have those sea breezes and land breezes, that can keep your temperatures closer to less extreme, I should say. Not as hot in the summer and not as cold in the winter. And big difference. Like there's been mornings, and I've used this in class in a normal school year where I'll show students, Rhinebeck in the morning might get down to 10 degrees on a January morning. It might be 10 in Rhinebeck. But you go to the South Shore of Long Island, it might be 30 degrees in the morning. So we drop down to 10 in the morning. Long Island's only 30. So they could be 20 degrees warmer on that same morning. Why? Just because of that ocean influence. Especially, like I said, south-facing shores of Long Island definitely see a big moderate living situation. California, go to places like San Diego. I mean, San Diego's become a very popular city. Why? I won't say easy living, but easier when it comes to weather. Not as hot, not as cold. It's a beautiful climate, San Diego. It's typically sunny and 75. They get some rain, but very little. And the temperatures are not extreme like we have. They don't have very hot summers and very cold winters. Their temperatures are more in the middle. And that's what they mean by moderate. People that live close to the ocean, large bodies of water, tend to have more moderate living. Not as hot, not as cold. And that's it for that. I'm going to stop there. This will be video number 1, and I will be working on a should be a shorter video for video number 2 this week. There'll be 2 videos this week. And I will talk to you soon. Bye.